Frequently in calculus we have to manipulate expressions like these, and these are called fractional expressions, so they're just the quotient of two algebraic expressions. And here we have the variable is x, we have a polynomial over another algebraic expression, and here we have another algebraic expression in the variable x, and in this case we have an algebraic expression in the variable h. And as we mentioned before, the variable is just a placeholder for a value in a particular set, so it doesn't really matter what you call the variable, as long as you know what the underlying set is, and as long as it remains consistent throughout your calculation. A rational expression is a quotient of two polynomials, and later we'll talk about these as rational functions. And here are two examples. It's a polynomial of degree 2 divided by a polynomial of degree 1, and here we have a polynomial of degree 3 divided by a polynomial of degree 2. And it's really important to master the algebraic manipulation of these expressions. The first thing we need to determine about them is to determine what the domain of such an expression is. So in other words, which real values of x make sense in this particular expression. Later we will talk about these expressions in the context of functions, and then the idea of the domain of the expression will become the domain of the function. So the domain of an algebraic expression is the set of all real numbers that the variable is permitted to have for that particular expression. So when finding domains, it's good to keep in mind that the square root of x is defined only for values of x which are greater than or equal to 0, and the denominator in any expression can never be 0 because you're not allowed to divide by 0. So for example, in this expression, we couldn't calculate this if we allowed x to be equal to -1, because then our expression doesn't make sense. We're dividing by 0. Let's try to find the domain of these two algebraic expressions. And again, I'd like to remind you that our restrictions are that anything under the square root sign must be greater than or equal to 0, and every denominator must avoid 0 values. So let's consider this expression, x over x squared minus 6x plus 9. How would we find the domain of this expression? Well, the first thing to do is factor the denominator here, so that we find the values of x which give us 0 in the denominator. So to take a shortcut here, this denominator should factor into the form x plus a1 times x plus a2, and the a1 times a2 should be 9, so, and a1 plus a2 should be minus 6, so it's going to be plus or minus 3 and plus or minus 3. We take the factors of 9, 3 times 3, and these add to 6, so we're on the right track here. However, we have to decide whether these are plus or minus. Both should have the same sign, because when we multiply we should get plus 9, and when we add we should get negative 6. So the only way that can happen is if both are negative 3. Now we see that in this expression every x makes sense except for those x values where the denominator is 0, and that happens only when x is 3. So the domain of this algebraic expression, or this rational expression, is all real numbers x such that x is not equal to 3, are all real numbers except 3. And formally we could write that in set theoretic notation. It's x in the real numbers such that x is not equal to 3. Let's think about the second algebraic expression. You might want to take a shot at finding the domain of this before I show you how. So we have two restrictions here. We cannot have x minus 5 equal to 0. That would give us a problem. That would mean we're dividing by 0. And we must have x plus 1 greater than or equal to 0 because we're applying the square root to x plus 1. And so this one translates to x is greater than or equal to minus 1. And this one translates to x is not equal to 5. So now our domain is everything else because everything else makes sense in this expression. So the domain is all real numbers greater than or equal to minus 1 and not equal to 5. So it's everything greater than or equal to minus 1 except 5. And if I want to write that in set theoretic notation, that's x an element of the reals such that x is greater than or equal to minus 1 and x is not equal to 5. And that gives me a complete description of the domain of this algebraic expression.